Where's my OBS instance? There we go. Everything's set up. Probably have a few minutes before people show up. Maybe I should like schedule streams. That might be better. Although, it's a lot of work. I'm kind of a spontaneous character. All right. Damn. There's like 15 layers of intuition I don't have. When's this assignment due? I don't think it's for a while, but yeah, there's a lot to go on understanding analysis, but I am starting to enjoy it a bit more. Analysis. I'm just checking when's this due. Assignments. February 28th, 6 days. All right, that's a while. What's up, Tom V8? OpenClaw hype? Yeah, I don't know. I don't know, honestly. Like, for me, yes, it's somewhat overrated. It's like, it still feels like quite brittle, and like, I mean, I love the theory so much, like just being able to like have agents crawl the web and do all your boring tasks for you, and like persistent memory, and like, I don't know, getting like a really good personal assistant is the dream, but it's just too many things feel like kind of sluggish with it, and kind of like syrupy and bad. I don't know. Like, it can just break in a lot of ways, and you have to connect like a cloud provider, and it's just like really expensive. You're just burning hella tokens if you don't have like some way around that, like an employer, or you can run a local model, and you need like good hardware to run a local model. And I don't know, like I think the idea is really cool, but overall, yeah, the execution like doesn't seem to be quite there yet. I don't, but yeah, I really want it to work. I started types from watching you. Would you advise me to, when I'm making notes, make it more beautiful? You mean like stylize the notes? Yeah, I mean, maybe. I don't know. I honestly feel like I'm just starting out learning types. Like, I know the basics, but I haven't done anything really crazy with it. And there's a lot that I want to do. Like, for instance, I had this idea the other day. You can see I have these like different definitions on the side. This is just like notes I kind of copied out of the textbook, and I was thinking like it would be really cool to have kind of like a cheat sheet generator that takes all these definitions. This doesn't really look like anything right now, and puts them on like a big board. So you have like a cheat sheet mode, but then you could use types to also have like a flashcard export mode, and then just render each of the pages as like an index card, and then you could like very easily print out every definition for your math classes. And I think just getting like the tooling around that working would be a very interesting project, and getting it kind of standardized, so like every math class you have, you could kind of fill out like a little form object that's like the definition, and then I don't know, a few alternative definitions, and it would like auto generate a cheat sheet and flashcards and stuff. And you could also like even do something like Obsidian where you have like a dependency graph going where you show how different math concepts relate to each other. What's up, Johnny? Good to see you here. Would you consider programming in C or in the future, or get into some low-level languages like Rust or Odin? I absolutely would consider programming in C. In fact, that's definitely something I'm going to do at some point. And for some reason, like Zig is really appealing to me. Like I just want to use Zig. And yeah, I feel like I haven't really gone through the pipeline of like severe low-level programming and making like a serious full project. I mean, like I did a rendering engine in C++, but honestly, that was like that I didn't take that as far as I wanted to. So I'd like to rebuild like maybe a small game or something using like OpenGL and Zig just to really drill the low-level concepts. I honestly don't use a fancy keyboard anymore. I'm straight back to the laptop keyboard, to be honest. Okay, so enough questioning. I have to get this analysis done. Yeah, analysis is, right now I'm on like closed, compact, open, perfect connected sets, and you can see I have the definition list on the side here. And so like I wrote down all the relevant definitions. There's a couple things I'm probably missing, like interior points and stuff. And then this homework is basically in regard to that. And yeah, to be honest, like my intuition for all this stuff right now is pretty bad. Like I just have some of the definitions in mind, and yeah. I mean, to quickly get sidetracked again. Oh, and how do I get the preview in the browser? It's all in my dot files on GitHub. There's a NeoVim plugin, and typed can do that too, I think. And why do programmers use different languages when C can do almost everything? That's a good point. Like, could just use C. The reason I think I would use Zig instead of C is like the build tools are nice, but I don't even know what I'm talking about. Yeah, all right. So let's look at this first problem. Basically, these are bonus point questions, but I'm thinking of starting with them because this first problem technically, if S is a subset of real numbers, prove that the interior of S is the union of all open subsets of Rn which are contained in S. And I don't really know how to start that, and I don't feel like I have great intuition for open sets yet, honestly. So just like this extra credit thing is like just 4 metric spaces, different distance functions, and then determining what each of these sets is, open, compact, or closed. So I feel like that's a solid place to start. But with that being said, there's like a little more to it than that, because these metric spaces, like they override the default definition of like epsilon neighborhoods, I guess, a little bit, or they just modify them, and I haven't really messed around with that a whole lot either. I'd say that my definition of interior, let me think, I should know this, is just all of the points in a set that aren't limit points. Yep, I don't actually have a definition for it. No, that might not be quite right, actually. The weird thing is, I don't think this book, Understanding Analysis, like defines interior except right here in this exercise. So it's like somewhat of an afterthought, which is funny. My professor included it on the homework, but it is what it is. The dual notion of the closure of a set is the interior of a set, and it's denoted as for all. What do they mean, dual notion with closures? Just the same thing? No. Because they possess a useful symmetry. So all the points are limit points. There exists oh man, analysis. Because that seems quite similar to like an open set. What do you mean dual notions? What does a dual notion exactly mean? Like the same thing? And isn't this just like an open set? Like, how is this definition different? The interior of a set. Oh. So I guess all interiors are open. So it's technically like you could take a closed set and then take the interior of it, and that would give you an open set. You can take a closed set, and all right, well, I'll worry about that in a second. Right now I want to worry about just determining whether, so we have metric space. I actually already explained this. So just the first question, determining whether this metric space, which is just the Euclidean distance and the integer lattice, is open, closed, or compact. And so open just means any epsilon neighborhood, or for any point in it we have an epsilon neighborhood that's a subset of it. Closed means that it contains all of its limit points. And compact means that every subsequence, every convergent sequence has a subsequence that's contained. No. The exact wording is like every subsequence of a convergent sequence is contained. Let me just check to see. Every sequence in K has a subsequence. So it's for all there exists. And this stuff is weird because I have like slight visual like a slight visual intuition about what open and closed means based on like an interval, but based on just like the reading I've done, that's like not quite what these things are. So like I have to build up what I actually understand these to be. You can define open sets in terms of closed sets and vice versa. So you can define the properties of one in terms of the other. Okay. Yeah. All right. So the integer lattice is interesting because I guess it's like it's just every point, every integer, x is in Rn, where xi and z for all I. So it's just all the, this is different from just this set of integers, because it's like higher dimensional, theoretically. Z of n. Well, no, I guess this just is the set of integers. Well, it's this set of n-dimensional integer tuples. So open. If this is open, it means an arbitrary point in x, which will be an integer. Well, yeah. Then we can take an epsilon neighborhood of it, and that will be in the set. And the epsilon neighborhood is going to be defined by Euclidean distance. So this might be wrong, but could you take like just the integer below or above it and say that's the radius? It's a little weird to me because like the integers are not continuous like the reals. There's like a bunch of gaps. For the first one, you have seen that compactness is equivalent to every open cover having a finite subcover. You can use that to show, I'm assuming, to those that the integer lattice is not exact. I mean, I've heard that, is not compact. I've heard that, but no, the definition is not especially internalized. That's what I'm trying to do today. Compactness is equivalent to every open cover having a finite subcover. Every open cover. How is that equivalent? That's pretty interesting. For the first one, the set is not open. Can you find an epsilon ball that contains a lattice point but is not a subset of the lattice? I mean, that contains a lattice point. Well, if the epsilon ball was like greater than or equal to 1 in radius, then you would get, like from an arbitrary x, you would get like an x plus 1. And that's a member of the integer lattice, but the like continuous range isn't a member of the integer lattice, because you like, I don't know, you get something in between those two x's, I guess. If that's what you're saying, like you could have like 1.5, and that's not in the integer lattice, but it would be which is but I'm not exactly sure that that's right, because our distance function wouldn't allow take the origin and consider the ball around it with radius 1/2. Right. Okay, so I think I get that. I'm just like making sure that the epsilon ball is basically creating like, it's creating a set that's in the reals, but we've got integers, so there's going to be a bunch of real numbers that don't. X in the reals. Okay. All right, I got you. All right, that makes sense. So this problem 1 since x plus 1 in so like the fractional yes, it's kind of topology, it's analysis, but metric spaces. So yeah, that makes sense to me. And then what about closure? Well, a set, the only sets that can be open and closed simultaneously are like the empty set, because of the logic, and the real numbers. So it's not closed, but just for the purpose of the exercise, like I'd like to see why it's not closed. If it contains all its limit points, I mean, could we find a limit point that it doesn't contain? Like, how would you prove something is closed or not closed? It is closed. Interesting. Show that the complement is open. And because the complement, the complement being open would imply that, because there's that property with complements negating open and closed. Oh yeah, yeah, not open and then closed. How's it going, really zen? Yeah, that's so is not open. That doesn't tell us anything about it being closed or not. Yeah, that is a careful. It's a good point to make. Um, so showing that a set is closed, showing that the complement of it is open. Why do that? Is that easier than so? Is that an easier way to prove that something is closed? It seems like so if something is closed, it contains all its limit points. So if you can find a limit point that is outside of of the integer lattice, then you will have shown it's closed. And if every epsilon neighborhood intersects the set at some point other than x, yeah, it seems a little tricky to show that a limit point because would you like take an arbitrary limit point and then try to show that that's not contained? Well, I'm getting confused from so it's not open. If we want to show that it's closed, we could take an arbitrary limit point and then show that it's in that lattice. So if you had a limit point, if every epsilon neighborhood of that x intersects the point at some other, okay. What if this set doesn't have limit points? In this case, I guess it's easier, but you have seen the equivalence of open if and only if not closed. No, I haven't. Showing that it contains its limit points kind of sucks. Okay, I much prefer taking the complement in general, but I think you're right in this case that showing closedness is easier. Okay, I'll keep that in mind. So in general, the complement method is better. Why in this case is it easier? I'm going to keep a note of that. Like, what sucks about it? You know someone's like a total math nerd when their username has arctan in it. It's easy to see that the limit points are just the lattice itself. Consider some epsilon less than 1/2. And then x minus xi is less than 1/2. But this forces... Right, because we can't take steps of 1/2. We have to take steps of 1. The limit points are the lattice itself. There's a limit point if every epsilon neighborhood I'm slightly confused by that. All the points are isolated points. An isolated point is not a limit point. That's the problem with YouTube chat. Like, we have Alfie Jones, 3850, and says that it's easy to see that the limit points are just the lattice itself. But then Arctan is saying all the points are isolated points. And I tend to agree that all the points are isolated points, because for a point to be a limit point, all epsilon neighborhoods have to contain or have to intersect the set at some point other than x, their origin. But that's clearly not the case, because you could say 0.2 and that won't intersect anywhere other. So all the points are isolated points. Yeah, I agree with what Arctan is saying here. That's a good argument. So basically, why did my scrolling get messed up on this? Closed since all limits are, or all points and points cannot be both. And then since we have no limit points whatsoever, it contains all of its limit points and it's closed. It's really zen. I've been trying to do it more in typed. I feel like typing versus handwriting, typing really falls apart when you have to do like complicated algebra, or there's like geometric arguments, and so in those cases, like I'll go to paper, and sometimes I just use paper, but it's easier to like visually stream typed, I think. And also, like, I just want more practice building up typed stuff. Like, I'm gradually kind of building like a bunch of aliases and stuff, and I just want to keep doing that and see like how far I can push a template into being good. There's one other thing I was working on too, which I think is really cool with types, is like this proof environment. You see I type proof like that, and it auto italicizes and colons, and then same thing with getting like the QED square, and that's done like through this regex expression. So you can like arbitrarily transform types syntax, and that's like the coolest thing I've been able to come up with. I guess also like the problems are auto bolding. Like I have a regex that auto bolds the problems. But I think like eventually, if I did enough of this typing and I got enough aliases, I could come up with some much cooler regexes that like just, I don't know. I guess another thing I'll say about doing math homework, like typing it, for real analysis, especially for like open and closed, a lot of this stuff is like, the proofs are kind of short, I feel like, and it's like, it's mostly conceptual terminology. Like, I'm trying to just apply like apply and understand like 5 different terms, and so I think it works. All right. Okay. So yeah, that was a very elegant solution. To arctan. And then, okay, now compactness. So I'm a little bit so compactness is basically every subsequence. It, like, if a sequence converges, then no, I have to get the order of the quantifiers right. For all, like, every convergent sequence in this set means that we have a subsequence that also converges to something in this set. Oh, unbounded, so can't be compact. Unbounded, so can't be compact. Okay, I believe you. I just want to like understand why. If every sequence has a subsequence, compact implies bounded. Why is that true? It's not bounded, but here it's quite easy to come up with an explicit sequence that does not have a convergent subsequence. Or its subset boundedness is required for compactness, not for generic metric spaces. N0000. Alright, it's strictly increase in magnitude. Alright, so it just 2 to the n just doubles every time. And Hein-Borel, but is not bounded, but I understand it's not bounded. Just why does that imply compactness? So we could have an unbounded sequence and it could converge to is the argument like that, well, if it diverges out to something infinitely large, that infinitely large thing isn't within the lattice? Something like 1000 or 2000, because 1000 sub Aziz. We're doing the first one and then we're trying to determine if that's compact. Well, we know it's compact. I'm just trying to understand why boundedness implies compactness and why unboundedness implies non-compactness. Someone said Hein-Borel. Right. We did cover this in class, yeah. I remember now. It's what not taking notes gets you. It was a long day, though. So I guess whipping out Hein-Borel is going to be necessary. Thanks for that. Yeah. So it's closed and bounded. And compact. Like, yeah. I believe this is true. I mean, well, this is true. It's just like I don't really have the intuition down, but I guess we could look at the proof of it briefly. It's definitely in the textbook, but let me just say on this question. All right. Hein-Borel. Right. And this is maybe a little weird. I remember my professor saying that like this is like Hein-Borel is technically not all three of these being equivalent. It's like two being equivalent, but this author broke it up in a weird way. The argument of not open is not right. Are real numbers minus the integers is open. This is understanding analysis. Stephen Abbott. You can get a PDF really easily by just Googling. That's a whole proof. It's the Heim-Borel theorem. In my analysis class, it took 2 days for 4 pages. Yeah. I mean, I so I really doubt that I'll have to prove this on an exam, but like I'd like to have the intuition for why it's true. I'm curious, like people in the really cracked people in the audience right now, the algebraic geometrists and stuff. Is this the kind of thing that like you remember, like the proof or the reasoning behind the Heim-Borel theorem? Like I don't need to fully know the proof technique, I guess. It's just like I don't intuitively understand why something being closed and bounded implies that it's compact. Well, I guess so. It's weird. I guess they're all kind of just the same definition. And every open cover for K is a finite subcover is also that's yeah, this is just one of those like three things all pointing their definition guns at each other. I would say going through the proof will give you the intuition. Okay, once you understand the proof. All right, cool. We'll do it. Yeah. All right, proof. All right, so we immediately get offloaded to another theorem. 3.3.4. Which is characterization of compactness. Compact if and only if it's closed and bounded. Okay. So it's compact, it must be bounded. So assume for contradiction that K is not bounded. The idea is to produce a sequence in K that marches off to infinity in such a way that it cannot have a convergent subsequence, as the definition of compact requires. Okay. K is not bounded, there must exist an element satisfying that x is greater than 1. Okay, x1 is greater than 1. And there must exist an x2 greater than 2. And in general, given an n, there's an nth element greater than n. So K is assumed to be compact. Should have a convergent subsequence x sub nk, but the elements of this subsequence should satisfy x nk greater than nk. By we set that up earlier with xn greater than n. And consequently x of n is unbounded because convergent sequences are bounded. We have a contradiction. So K must be a bounded set. Okay. To see that K contains its limit points, let x equals the limit As x approaches n, where xn is contained in k, and argue that k or x must be in k as well. Definition 3.3.1, the sequence has a convergent subsequence. And we know that it converges to the same limit. Okay, I don't fully buy that, but god damn it, there's such a dependency chain here. Outrageous. It's like (5.2.5.2) because they converge to the same limit. So a subsequence converges to the same limit as the sequence. Okay. So I feel slightly better about that, but I don't know. Still, I think I have to stare at this for like 3 hours. That doesn't make the most entertaining stream ever. So let's get back to solving these compactness exercises, and I'll go on the I'll just go on the little loosey-goosey definition for now. Okay, so now we got the cone. So the cone is so we have a point in Rn, and the way this is formed is that the nth part of the point is greater than all the previous multiplied together. Overthinking your message to a YouTuber you feel slightly parasocial to is ridiculous. That's really funny. Definition of the cone looks a bit funky. Seems like it only contains the axes. Also, the definition of the metric seems to be missing a square. Oh no, you have a fever? Sometimes I kind of enjoy the feeling of a fever. I don't know why. Let me double check my... Oh, yeah. So I did totally miss a square. I don't know how I didn't notice that before, because otherwise this is just like not a correct distance function at all. So where is that distance function? Oh, it's right here. That just needs to be squared. All right, and then the cone... is the cone definition funky? I mean, no, it's fine, other than like I omitted the 2 subscript on the distance, but I don't know. Yeah, copying down problems wrong is like a real hazard of the occupation for sure. I don't understand your argument about Zn being not closed. Sorry, not open. You don't understand it not being closed. One sec, I gotta verify. All right. Yeah, it's not open. It is closed since all points are isolated points, and they're isolated points because they're not limit points, and limit points means that they intersect, or every epsilon ball drawn around them intersects the lattice at some other point. But oh, a ton of ice just fell in someone's car out there. But you could say x, so x is your thing, and then you draw a ball with 0.1 radius. And then that violates that. So it has to be an isolated point. And you can't have points aren't both isolated and limit points. And therefore, you have no limit points whatsoever. So it contains all 0 of its limit points, so it's closed. You have it backwards. Oh, TZ. The not open argument is not correct. Not open. Oh, the not open argument. Is that true? If all points for all points there exists an epsilon neighborhood. I mean, wait, isn't this fine? This is an arbitrary point x, and then this is a specific epsilon neighborhood. It's existential, and then you have like half of that isn't contained. One particular ball isn't contained in the set. Wait, I'm confused. So that argument seems valid to me with my understanding of how the quantifiers work, but the negation of that statement. The negation, tricky. Open requires at least one open ball being fully contained in the set. The negation is that there exists no ball that is fully contained in the set. Oh yeah, that one is, you're right, that's not good. I'm thinking about it in one dimension. Like, I'm just saying the radius of the ball, this is the epsilon, but that doesn't really make sense because we're in n dimensions. And the distance function is that. So I guess that argument isn't correct. At least one ball being fully contained in the set. It's not so much the dimension as it is just using a counterexample for something that needs more. Open says for all points you must have at least one epsilon neighborhood contained fully in the set. Right. Yeah. You must have at least one epsilon neighborhood. But right, it's not enough to show a counterexample. Right. Alphosis. X plus x1 plus epsilon halves x2 xn is not in the lattice for all epsilon less than 1, but it is in the ball radius epsilon around x, therefore there is no ball. So not open would mean for at least one point. What are my neighbors up there doing? Hopefully that's not too audible. So not open would mean for at least one point you must have all epsilon neighborhoods are not contained in the set. Right, to negate the quantifiers. For at least one point, you must have all epsilon neighborhoods are not contained. Remember that you go from a definition, then you take the not of that definition. Right, it requires inverting all the quantifiers. Yeah, I guess I'm a little confused, or I forgot to do that because trying to like verify whether or not it's open. We just kind of set out trying to prove that it's like the problem wasn't necessarily that, but okay. So not open since so you would take a point, let's say since 0 in the reals, or well, yeah, since 0 is in, it doesn't really matter what point we pick. We just have to show that all epsilon neighborhoods aren't contained. Which is going to be true because there's a bunch of real numbers that aren't integers. But how do you say that exactly? Let's see. x1, so an arbitrary point. Well, yeah, it doesn't really matter. Plus epsilon halves is not in the lattice for all epsilon less than 1. Yeah. But it is in the ball radius. But for the negation, alphosis, like, I'm a little confused by that because, like, I get what you're saying with the epsilon over 2. As long as you've got an epsilon less than 1, you're going to get a fraction. So that's not in the lattice. But don't we have to show that for all, for like any value of epsilon? As for all analysis proofs, let epsilon be greater than 0. Then show the epsilon ball is not contained in the lattice. Even if epsilon is greater than 1, your ball will not be fully contained. Right. Yeah, okay. Min epsilon over 2 and then 1/2. Any large epsilon ball containing all smaller epsilon balls. So it's fine to say something like epsilon less than 1. Oh, that's really brilliant. Yeah. Thanks. That makes a lot of sense. Yeah. Yeah. So saying like x1 plus yeah, wow, I didn't really consider that. Right. Because that intersects at x2 for sure. Just trivially. And but so should I just say at x2 but what we're doing is exhibiting a point inside the epsilon ball that is not in the lattice. Therefore, the ball is not completely inside the lattice. And What we're doing is exhibiting a point inside the ball that is not in the lattice. Yeah, this is... now I understand this argument pretty intuitively. I just want to figure out like how to write that up formally. So if we let... but that... Oh, it's not an equal subset dot equal dot not. That's janky. For epsilon less than 1. And that's fine because any larger epsilon ball will also contain that smaller epsilon ball. Yeah, at what point there exists integers between reals? Yeah. So, and honestly, like to be fully transparent here, this professor like is will give like a lot of credit for just like broad strokes things, and she's not like incredibly concerned with like technical details, maybe as much as she should be, honestly. Like I kind of prefer stricter graders, but and this specific segment is like an extra credit assignment, but I thought it would just give me better intuition. But it's also like I don't know, dude, there are people in that real analysis class, like there's this girl who sits next to me that straight up like watches Instagram reels in class, which is insane. And like yeah, I have no idea how she's gonna pass. Maybe just has like an insane IQ, I don't know. Okay. Assuming that's all right. Passive absorption. Suppose Z n is open, then there exists a ball of radius epsilon less than 1 around 0 contained inside the lattice. This is a contradiction due to the point. Yeah, we all know she's getting a better grade than I am. So you've got a Zn, and you're supposing it's open. Then there exists a ball of radius 1. There was some other girl actually too, like I don't know if she's like a brand manager or something, but she was like had Instagram up on her laptop and was just like bookmarking like tons and tons of random fashion posts like in the middle of class. And real analysis is like if you zone out for 30 seconds, it's over. So I don't know how that's, and also like there's an absolutely rampant amount of like people just using AI to like explain their homework to them, which is like, I mean, super degenerate. Like I have human grad students explaining this to me. Immensely different. Yes, a stream of people is nowhere near. Okay. I guess let's move on to the cone. The cone. So, I know Johnny dropped a bunch of cone wisdom earlier on. The cone. Is the cone open? Does an arbitrary ball inside the cone or for every point in the cone can we draw an epsilon ball? I mean, yes, right? Because couldn't you just say just draw an epsilon ball like that's like the minimum of, because you have that it's less than an x of n, which means that you have its distance from the two kind of sides, well, n sides, and so there exists like no matter what point you pick. Well, what if you pick like a point on the edge actually? Because that's less than or equal to. I think the cone definition seems off. It seems like it's just one axis, which seems weird. I'll check my copy of the homework. The cone. Oh. Oh, yeah, that is wrong. Well, no, it's not actually. Well, there's a missing comma, but so they're not multiplied together. Just what do you mean there's a missing axis? That's definitely what the assignment says. Throw it up next to it's the same cone. Pretty sure. Just take the origin. It's not open. And by taking limits on both sides of the inequality, we can show that it's closed. Taking limits on both sides of the inequality? Okay, just think about 2D. This thing boils down to the absolute value. Oh, you're right. Yeah, it does boil down to the absolute value. That's what a cone is. It's less than any of yeah. I guess we're doing not open. And so just like so if you have a point 0 and then negative epsilon halves, that'll never be in the cone. Right. Okay. So to prove that it's not open, we need the negated definition of open, so that for an arbitrary point, all any epsilon is not contained within the cone. And why is that? Not every point will lead to a contradiction this time. So, if you pick the origin, there's a point negative epsilon halves why is negative epsilon halves never in the cone? If it's all zeros and then negative epsilon halves, Man, I'm trying to even conceptualize like what. Yeah, so just in the simple 2D case, that's just when x2 is or x1 is less than x2. Right. It has a negative x coordinate, which is not possible. Like, because that's just the absolute value function. And, yeah. Pick a point where the inequality is actually an inequality. That'll give you a contradiction. And so, just saying 0, 0, dot, dot, dot. Negative epsilon halves. Means that the distance and the distance around all of this that's not possible because you get something positive less than something negative. Okay. Right. Try and picture a ball centered at the tip of a cone. Okay, yeah. And it's clearly not inside the cone. And just to make it formal, pick a point. And is that the point in question? No, the point in question would be 0, 0, 0, 0. This is like a random point off to the side and underneath the cone. Well, not off to the side. I guess it's just like underneath the cone. But tip of the cone is all zeros. Wait, but isn't that within the cone though? Because like using the inequality, if you have just like a bunch of zeros, and then this is just the distance between all the zeros, like that's within. If the cone were open, there should be a ball of radius epsilon also in the cone, but all such balls contain... Ah, yeah. Right. Yeah. If the cone were open, there should be a ball of radius epsilon also in the cone. Right, okay. I see that. Well, it doesn't contain. Yeah, I appreciate it. Alphosis. Interesting name. Okay, all right. I slightly understand this better now. So you've got the Rudolph nose at the end of the cone, and that's inside. But wait, why is it why'd you pick negative epsilon over 2 and not just negative epsilon? For all x in the cone, there exists an open ball of radius epsilon centered at x inside the cone. Not open. There exists a point where an open ball of radius epsilon is not fully inside the cone. To guarantee it's actually contained in the epsilon ball. Gotcha. Right, because the epsilon ball is less than and not less than or equal to. No, I didn't name a file Zathura. There's just a PDF reader called Zathura. Okay. Is that... So the negation, we have a specific point, 0, 0, the tip of the cone, and that contains 0 and epsilon halves here, which is not part of the cone. And when you say not inside the cone, all that you really have to do is say, like some of it can be within, like epsilon halves is in the ball, just not negative epsilon halves. Yeah, alphosis is, yeah. To prove A is not a subset of B, we just find a point A not in B, right? Very cool. Yeah. Man, math is awesome. That's so sick. How cool is it that we can stream video across the planet of a guy using Vim to do math and bond over a theoretical set of axioms that are like basically divorced from reality but model things pretty well? That's incredible. Okay. So that's not open. And now to say that this is closed, V-enhance on YouTube, okay. Well, I'll put this in my... Yeah, for sure. Appreciate you stopping by. I appreciate everyone who's got math skills that's willing to spare the time. Because it's definitely like... I wonder if it's like frustrating sometimes, because obviously these concepts like can take quite a long time to like build an intuition for, and so I appreciate you bearing with me struggling through this. Okay. All right, Big Pepe has an idea. Show the code is closed, we can do this. Let P sub k equal xi sub k, I between 1 and n, be the sequence of points in the cone that converge to P. Okay. And okay, so you're setting up a sequence that converges to P, and we know that the nth term of the sequence, well, the kth, x sub n sub k, is at least that distance of all the previous points, and then take k to infinity. All right, I'm interested in what you're saying there, but I want to build more intuition for it. So you set up a sequence of points in the cone. That converge to a point P. How do you know they converge? We know definition of closed means convergent sequence must converge inside the set. Wait, I'm confused though, because aren't we trying to show that the cone is closed? Are you just going to assume that the cone is closed and then... Yeah, but we're trying to show that the cone is closed, but you're assuming that it's closed already. Thanks, Arctan. Thanks for all the answers. One of the arts that plays dividends in numerous other facets of life. Confusion now is an idea later. Thanks. Yeah, you're absolutely right. Okay. Showing it's closed. Okay, so no to show closedness we consider the arbitrary sequence in the cone. I think you're saying the same thing as Big Pepe. We have a sequence pk that converges to p. We want to prove that p is in the cone, given that pk is in the cone. Oh. Okay. All right. Closed. So you have an arbitrary sequence. We want to show that that pk converges to p, which is in C. And how is that actually... Given a convergent sequence in C, we want to show that the limit well, it's convergent. That what convergent, an arbitrary convergence sequence. Okay. Show that what PK converges to is in the cone. Okay, and to show that, we just want to show that for that there exists an epsilon yeah, welcome Arctic. Good luck with your studying. So now to show convergence, we need to find an epsilon. Well, no, we need to find an n, well, a k, past which k for any epsilon is less than that distance function we're given. Oh geez. Okay. So we need to find some epsilon that this will be less than no matter what. And we have that basic inequality. Oh, what am I doing? I was just thinking for so long, like, how do I prove this is convergent? And that's literally given. What we have to do is prove that my brain is fried. That this that PK convergent sequence to we want to show that what PK converges to. Just call that P, is in C. I'm kind of confused on how to go about saying that's true. Okay. We got a couple banger answers. First of all, Big Pepe with a limit point. Okay. So we have p equals a limit point, and we need to show that xn is at least we have to imply xn is at least that, which will imply that it's in there. Okay. And then Johnny says this is if the limit were outside the set. Okay, then it would lie some epsilon distance outside it. And thus, if you go far enough along in your sequence, the points past that point would also lie outside the set. But this is basically just saying that the complement is open. The complement is open. Because you're saying outside. Man, that's weird. I really like Big Pepe's answer here, but like it seems. How would you know? It seems like you're both taking different like approaches, because saying the complement is open. Someone said earlier that's generally easier, but yeah, this seems converges to some p equals x1 ... x n minus 1 is in C. But and we want to show that that x we want to show the distance of that x or that point, basically that point from each other is less than xn, less than or equal to xn. And it's the sum of all the squared. Okay. Help to draw a picture in 2D. All right, I'll do that in a sec, but do you know the fact that if two convergent sequences A and Bn such that An is at least Bn, then the limit of A is at least the limit of B? Here, An and Bn are real numbers. So you basically do that here. This is also needing that the distance is continuous. But that's fine. With Big Pepe, I'm confused what you mean by if you have two convergent sequences, An is at least Bn. We don't have two convergent sequences. I mean, we have one. You saying like have another convergent sequence? Basically, our AN here is the last coordinate. Bn is just the norm of the first n minus 1. Yeah, this subject is under AI. If you don't understand the sigmoid squishification function as a monotonic increasing continuous function, then you're basically never going to understand GPT models fully. Analysis is required. Okay, and n is just the norm of the first n minus 1 coordinates. What do you mean norm? AN here is the last coordinate, and BN is the norm of the first n minus 1 coordinates. Man, this is... sub zigzag. It's we're trying to prove that this cone is closed. Okay, so apparently Big Pepe's solution is awesome, but the norm of the first n minus 1 coordinates. So you have two different convergent sequences, and one of them is converging along n minus 1. Yeah, I'm all in on Big Pepe's answer. I just want to fully understand it. Okay. Okay. Norm of the first coordinates. Oh, the magnitude or length. Oh. So this is the norm, basically. So the norm of the first n minus 1 coordinates norms and trees. Hmm. 1% increase in IQ points or triple the size of your dick. That's a tough one. Actually, metric is induced by a norm. Did you understand my solution? I'm in the process of understanding your solution. So you have two sequences. One is the norm. One is the norm of the first n minus 1. A is at least bn, then the limit of A is at least the limit of bn. An is the last coordinate. That's extremely big brain, but okay. So there's, I guess I should break this down into like what I'm specifically confused about with your solution, instead of thinking about it in my head. So you're saying we have two different convergent sequences, and then using that property that one is greater than another, that'll give us the algebraic resolution to this that'll show what we need to. But you can create a sequence that's like moving along different kind of dimensions, I guess, in the space is what I'm somewhat confused about. Like one that moves along the norm of the first n, and then one that moves along the last. Like that's, so I guess I'm slightly confused about the ability to like to construct those with those kind of constraints. Like I see how the algebra would work out, because if you have if you have an and bn, that's very nice, and then you can just substitute in exactly what you need. You can substitute in that you're the norm of, wow, that dude, that's fucking brilliant. Oh my god, how did you come up with that? And I see how the algebra there is like just beautiful, but so I'm just still a little confused on this converging to two arbitrary convergent sequences so if we have two convergent sequences, you need to say that the norm is continuous, otherwise you don't know that the limit bn is the same as x1 xn minus 1. You don't know that it's the same. Hmm. That's interesting. So just like how do you say this when you're constructing those two sets, or when you're setting up those two limits like that, or two sequences, you can generate arbitrary convergent sequences, and then say that just one is bigger than another, and say that one is convergent along that's just the part that I'm kind of confused about. Like, what exactly am I saying here? Uh, like, okay, I'll just write out kind of what I think this is, just for the sake of not getting too caught up and stuck on this. Um, so, like, 1 n minus 1, or 1. And now b b converges to you do it, you're saying, on the last like, I don't exactly know. Oh yeah, gotta make sure to say a and b n in C. Closed is that it contains its limits. Think of the difference between 0, 1 and 0, 1. Trying to show that cone contains its limits. I mean, yeah, I think I understand kind of the high-level execution here. We have a sequence of points in the cone, each of them individually satisfying that Right. Like, yeah, I get the high level execution. I'm just not sure what Big Pepe says or like means rigorously by having limits like converging to um, like the norm of the first n coordinates and then the last coordinate. Um, like just how is that set up? Yeah, yeah. I get exactly like that's I'm not stuck on any of that, and I understand this lemma. But what specific sequences are we saying here? That's what I'm confused about. Like so, like what sequence will result in what we're looking for? Specifically, that the norm is less than the value itself. Okay, thanks, Johnny. You should start by assuming that we are given some arbitrary convergent sequence in the cone, and then we build two new sequence. We have the sequence index and the coordinate index, right? And the other is the norm of the first coordinates of the original sequence. Two new sequences. Yeah. Um, but if we say we have a sequence x sub or xa with components um, x1 up to xn, then there's a sequence um, AA and BA. And AA is the nth, and BA. Okay, yeah, that's all I was really confused about. So, um, just like creating a sequence and then breaking it into two other sequences. Um, uh, yeah, that's yeah. So an arbitrary convergent sequence, like C sub n, that's cursed. That's really cursed. D sub n. Which equals Yeah, this is just like messed up because like you got it's like a sequence over a tuple. There's like different component parts to it. So so each one of the it's weird, I guess, because so this tuple of points is converging. That the whole tuple is convergent, and then the like you can take subsections of that tuple, and each of those is also convergent. Importantly, n is fixed, the dimensions, and then the index I used as a is the sequence index. Yeah. Jeez, this is mind bending. Yeah. Converging to x1 xn, can break it into two sequences an and bn. A and C equals the norm well, I'm not gonna put that in there. And Bn and C such that this is redundant actually, because we're breaking it into the two sequences. Just that A equals x1 and minus 1 and B just equals n. Oh man, I just feel dubious about this. Like yeah, you're confused about coordinate indices with sequence indices. Yeah. You're confused about coordinate indices and sequence indices. Yeah. Number of entries. And b equals n. b equals n. What should be? Right, it shouldn't change with its, yeah. So, like, I guess, should we introduce, like, another, b sub k, a sub k, b sub k. I mean, this technically, I guess, needs to be double indexed. And oh, not n. Think of x sub I times k as a function that gives the ith coordinate of the kth term. If you say that we have a sequence xa, A is the sequence index here, with components okay, xa1, then there's the sequence ba equals xan. Oh, and aa equals, oh, thank you, Alphosis. That explains things way, yeah, I see what you're saying now. I'm just going to rewrite that. Convergent sequence, xa in C, which equals, so I'll put parentheses around that, equaling x1 up to xn. We have two component sequences, x BA, which equals XA sub N, and AA. So this is like kind of hurrying along the A to the other sequence. Which is norm xa sub 1 dot 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 xa sub n minus 1. Jeez. Unexpected argument? What's unexpected about that? Okay, so we have those two sequences. Great. I think you want xan not in the way it is rendering. Oh, xa sub n. Like that. Yeah. I see. Man, that's some tricky fucking shit. Okay. God. Okay. So now we've got those two components. And thanks a lot, Alphosis. That was a really good way to explain that. And then XA is in the cone. XA is in the cone. B BA AA. Let's see. Do I fully buy that? Do I fully buy that? Yeah. Wow, that is a really clever solution, honestly, to break the sequence into those two component parts. check Discord. Johnny has sent me something. Let's see. Outline for the argument. All right. Here we go. Thank you, Johnny. All right. Suppose pk sub k is a sequence contained in the cone which converges to some p in right, it converges to some p in the real numbers. Now define sequences a sub k and b sub k, and in the reals, where k sub I j is the ith coordinate of pk. Since pk is in C for all k, we have that AK is greater than or equal to BK. Now going fast. Right, P equals x1 to xn, then the limit of BK and the limit of AK equals xn. And then since the limit lemma, okay. So, yeah, I almost fully understand this. It's just the only part left is the limit of k, like this part. Since pk is in C for all k, why is that necessarily true? Okay, I have to narrow in on that. That's honestly like the very last thing that is confusing me about this. Where is the jth coordinate or ith coordinate of pk? Yeah. Just the fact that A is greater than B isn't fully obvious to me. But oh well, I'll look at that again later. But just to complete this, since lim we have that. All right, back up the fucking abstraction stack. We have that this. We have that our arbitrary limit point is within C. In C, so C is closed. Okay, slightly sloppy. There's a little stuff I don't understand there, but you know, can't. Sometimes you just have to move right along. All right. I'll make this a comment. It would be awkward if my professor saw the. Oops. Oh man, that's horrible. Can't switch back. Vague. There we go. PMaster Big is spouting some topology nonsense. No, this isn't topology. The fact that AK is bigger than BK follows from the definition of the cone. Thank you, Johnny. Saving me as always. Jeez. Okay. Now let's hopefully these just get faster as I go, but the open unit, oh, actually, we still have, is this compact? It's closed. Is it bounded? Is there something for which everything is less than it? So using, well, there's a couple ways to go here, I guess. Showing that it's bounded will show that it's compact. And every open cover for K has a finite subcover, which is equivalent to showing that every convergent sequence has a subsequence that also converges. Okay. And you can arbitrarily enlarge your final coordinate. You can arbitrarily enlarge your final coordinate meeting xn. Right, yeah. You can always just make that bigger and bigger. Yeah. Do I see why it's not bounded? Yeah, I mean, because the xn, the last coordinate, or are you talking about xn minus 1 as the last coordinate? xn, right. And because in the inequality, like, you can just always jack it up to bigger and bigger and bigger and bigger values, and you still preserve the cone. What definition is the class using for closed sets, isolated and or limit points? I mean, I have all the definitions written down here. Closed sets, I think they just contain all its limit points. Isolated are just not limit points. Limit points are I mean, they're literally the point where a sequence in the set converges to. In other words, like, they have an epsilon neighborhood around them where that intersects. Yeah. Limit point of a set if every epsilon neighborhood intersects that set. Every epsilon neighborhood. Not that they have one, it's that every. Okay. Those are the definitions. Yeah, okay, and I see that. All right. Cool. I was laughing earlier. It's really funny when people will show up for like a brief minute, and then like, the question I see all the time is like, what's your major? What year are you in? What type of math is this? People just like want to ask that and leave, which is interesting. But I appreciate the like 5 people that consistently stay around for hours. Oh my god. Ugh, my tea bag broke in there. That was horrible. It was all like leafy. Ugh. All right, I'm gonna go eat some food for like 5 minutes, and then I'll be back. If anyone is still interested in solving these problems, next up is going to be the open unit ball. So break break.type. Let's create a persistent break. I want to break eating food. Okay. Set page width 5 inches, height 3 inches. Set align center plus horizon. Set text. Well, it's actually fill black. I'll change the style of this every once in a while as I build this up. Fill white. Sure, that's a good font. Size 40 point. Sure. I'll style this differently, which is funnier. Okay. All right, I'll see you guys in a sec. Dude, I should not have said that to Allison. Alright, what did I miss? Hyperplanes are not open. Alright, I'll worry about what that means in a minute. I think what I want to do, just as this stream tradition, because I'm trying to get into being an internet degenerate, break. I want to add like some content to this every time I take a break and see if it can get decorated eventually. Does someone have like a favorite equation that you think is like really elegant? I'll get to that in a sec, Big Pepe. What's like what do you think is the best? Oh, 2 + 2 is 4. Shit, yeah. That's pretty fundamental. Okay, you're getting on the board. Pajama Man. Van Kampen's equation. Okay. Theorem. Please no algebraic topology. If anyone can show this problem with Van Kampen's theorem, they'll get a cookie. The diagram might be rough to type. Yeah, I was just thinking that. God damn it. How am I supposed to type that? That's outrageous. Yeah, I'm not typing that out. There is a types package for commutative diagrams, but I don't want to spend like 3 hours whipping up unless someone has already done it. Types. Nope, I don't see it. No, it's got to be I can't just do that. I have to type it out. All right. For this one time, I'm just adding place bottom plus left, and then we'll start adding math around. Do the simple classic. It's going to get a new equation each time. All right. Enough brain rot. Enough productive slacking off. The hyperplane. Well, technically, we're on question 3, the open unit ball. The open unit ball. I mean, it says it's open. I think the open unit ball might be open. Yeah. I mean, let me just. What's the epsilon neighborhood going to be though? 1 over like 1 over x? Or 1 over well, what about like the min of 1 and epsilon? Thinking about everything in 2D is the best way here. Okay, alright, thanks. Alright, thinking about it in 2D. Well, take epsilon as less than the distance from the boundary. And the distance from the boundary is like x squared plus y squared less than 1. That's the distance of a circle. And it's less than that distance. So what epsilon? Just so I... But epsilon is going to be like in terms of so take epsilon less than 1 minus p. Then the epsilon neighborhood is the open unit ball. 1 minus p squared. Shout out Brown Coyote. So the epsilon is less than epsilon one minus absolute value of x1 Oh. So this is the distance from the edge. The distance from the edge of the ball is just 1 minus the distance of a point from itself. Okay. There's a value less than the distance from the edge. Open unit ball is the one centered at the origin. Draw a 2D picture. Right. Okay, wow. Opening Figma like is laggy. Yeesh. Figma's not even opening. Loaded Electron app. Okay. So that's our unit ball in 2 dimensions. And how do you change colors? Wow, what a nice app. All the hotkeys. And like the distance of a point to the edge is just like that. Well, is there a way to make this thinner? Actually, I would rather just draw on paper. This is not... What? Why does this have like a split in it? Can you move the different parts of this? What is this? This is heinous. We're just dealing with, in 2 dimensions, this unit ball, and the distance is just 1 minus the distance of a point in here. So you say 0, 0. Back to what Big Pepe was saying. About... I guess I'm confused. Why is this expression the distance oops, oh my god. Why is that the distance from the edge? Well, I guess the distance from the origin to the edge will always be 1. So it's like that distance, like that's just what this is saying. The 1 is saying. So it's like the distance from the origin to the edge minus the distance of, like, this is just kind of a collapsed, simplified statement, I guess. Like, this is like minus, well, distance of 0, 0. The distance from the edge to the origin minus the distance from a point to the origin, yeah, would leave you with the distance of the point to the edge. Okay, so that's just challenge that solves the problem. Draw a circle centered at a movable point. Challenge that solves L2 minimizer. Draw a circle centered at a movable point in the circle that stays inside the circle. Challenge that solves the problem. Draw a circle centered at a movable point in the circle that stays inside the circle. That actually is an interesting question. I wonder if it's like possible to quickly make something like that with Desmos. So can you get a point and have it draggable? And then we have to clamp these points to within the circle. Which, is there a way to do that? Can we do a squared plus b squared less than 1? Oh! Okay, we have to move it with sliders now, I guess. Label. No, you can't drag it around. Wait, can we make the sliders like this is, I don't know about this. This is very janky. Okay. No way. 0. Well, actually, we don't want that. We want negative that. And then copy that. Make that an A. Squared. Does this not like invalid slider number? Try using any number. Why is that not valid? And then can we say this is less than 1 minus A? Yeah, we're not allowed to double reference like that, which is unfortunate. This is ridiculous. This is Desmos programming instead of solving the problem. But it would be sick to have a draggable point that is always less than. Okay, maybe Not worrying about the bounds for a second. Well, those bounds are fine, whatever. What about like a circle? How do you do this again? Like x minus a squared plus y minus b squared? Equals 1 or less than 1. So there's a movable circle. But how would this like ideally this would shrink to stay inside. You're cooked, son. Have fun with your homework. Ideally, this would shrink to stay inside. The other circle is less than, so this should get smaller as we get farther from 0. As we get farther from 0. So as the distance from 0 of A and B increases, that's not really right. As we get farther from 0, yeah, you want to adjust the radius dynamically. But what is the equation for the radius? Less than the distance from the boundary. Like that. It's close. Less than the distance from the boundary. No, I'm honestly not sure this is at all helping me understand the problem. I'm just like enjoying the Desmos programming. Less than the distance from the boundary. This is closer, but it's not there yet. What is the distance from the boundary? Is it this? Oh my god, Desmos is so annoying. One minus a squared 1 minus b squared. Fuck. Okay. This is so damn fiddly. No. It's less than x squared plus y squared equals 1. Review the equation for a circle. Yeah, isn't this just less than 1? No. Well, equals r squared. Equals r squared. What's the expression for r? Is the x squared plus y squared minus one minus circle centered at AB with radius r is a set of points x, y such that a minus x, yeah. You can write r equals f of AB for an appropriate function f. Yeah, and r is going to be what exactly is the distance from here to here? I mean, it's the distance, it's this distance, it's 1 minus this distance, which is a squared plus b squared. That's what I had before, wasn't it? But a squared plus b squared. That distance minus that distance. And that's the radius, but that doesn't seem right. It's that distance minus that distance should give us a radius of that. Oh, equals r squared. Do we have to put this whole thing to the... No. There we go. Oh, that's satisfying. Okay. That's so sick. That did not help me understand this problem or how to solve it. I feel like I already kind of knew what this looked like, but the algebra tripped me up. But yeah, dang, this is really enjoyable. Yeah, circle is in another circle. The circle is the other circle. Okay, I gotta stop messing with that and actually, so having the formula for the radius should help you. Well, the radius is is 1. You mean in terms of Well, okay, so basically all we have to say here is um, if this is the distance from the edge, then all we have to do is say epsilon equals the distance from the edge cut in half. Right? I mean, like can't you just say, okay, here's any point and the distance from the edge, like half the distance from the edge is gonna be within. It's in there. Okay. I don't think I have to super like do this extremely rigorously. I guess it would be good practice, but I believe I would get full credit for that. What do you mean you don't need distances technically? Okay. All right, then is this closed? We could show the complement is open. Oh, you don't need to have the distance. Well, wait, don't you need to have the distance? Because if you don't, then you get it like directly on the border. Okay, but closed. This is a case maybe where we could show the complement is open. Well, actually, we don't want to show that it's closed. Or well, it's not closed. It's open. So we could show that the complement isn't open. Showing that the complement isn't open complement isn't open. meaning that oh my god, this is just layers and layers. So, meaning that the complement which is x greater than 1 isn't open, which means that there exists an element in there where every epsilon neighborhood is a subset. Man, my working memory is like very tired out. Showing the complement is not open seems to be an extra step for no reason. You think it's better approach to just prove it straight? Another way to say this would be it contains all its limit points. A limit point which is not part of the unit ball. Every epsilon neighborhood intersects at a point other than S or other than X. If every okay. What about like 1, 0? Well, I guess, yeah. There's the two different definitions. I was trying to think of one where every I don't know. You can see it right under me. Where every epsilon neighborhood intersects A at some point, and I guess they're equivalent. And but the sequence 1 minus 1 over n a limit point which is not part of the unit ball. You can explicitly exhibit a limit point which is not part of the ball. Zero, zero, 1 over n. Zero, zero, 1 over n. Every epsilon neighborhood intersects the set A at some point other than x. This picture is a lot clearer if you've seen that any subset of Rn partitions Rn into 3 pieces: the interior, the boundary, and the exterior. Yeah, the interior, the boundary, and the exterior. This is open when the boundary is outside S, and S is closed when the boundary is inside S. I'm going to copy that down. If it is neither, the boundary, if it is neither, the boundary is partially inside and partially outside, and both of the boundary is empty. Proving it is actually very difficult, even though the solution is I think you're talking about something else. All right. if every sequence, no. It's an isolated point, or a limit point. Wait. I'm confused about Johnny saying a little while ago, and other people, the sequence 0, 0, ... 1 over n lies in the unit ball, but its limit does not. The sequence... What do you mean 0, 0, 1 over n? What are the intermediary terms? Just all zeros and then the last term is 1 over n? One minus 1 over n. Oh. Man, I get confused by like the tuple. Goddamn tuple stuff. Okay. I see what you're saying. I thought you were like detailing every element of that sequence, but so why does 0, 0, 0? That seems like it lies in the unit ball. Wouldn't you want something that like converges to 1? Oh, that's what Alexander was saying. Oh, I see. 1 minus 1 over n, because 1 itself is on the boundary. Oh, I see. Sequence, boundary, but it's okay. Yeah. I see. Yeah. Wow. Well done. Well thought out. God damn it, Johnny. Even you get stuff wrong occasionally, I guess. And then this proves the ball isn't closed, but that doesn't mean it's open. Well, we proved it's open earlier, because for any point you could say that half the distance, like your epsilon is half the distance to the edge. Not super rigorous, but I think intuitively. Okay, and then this is bounded, and it's not closed because it doesn't contain all its limit points. It's not compact. Okay, the hyperplane. Yeesh. The openness proof is similar to the Desmos coding. You want to show that each point in the open ball is an interior point by drawing a smaller ball around it that's still contained in there. Yeah. Oh, yeah. The equivalent of vibe coding. It's being like a grad student in math is just insane. You're like in the 0.00001%. And then you're like, I can't solve this really abstract thing. I'm so dumb. But that's just how it is. There's always a moving target. Okay. The hyperplane. Is the hyperplane open? First of all, what is the hyperplane? Is a point such that some constant times the point equals another constant for a fixed constant that isn't zero. Wait, how do we remove zero out of like an n-dimensional thing? A is a vector minus the zero vector. Oh, because A is in there, yeah. Okay. Dot product. It's the orthogonal complement to some non-zero vector. So you're pointing somewhere and it's like, it's at a 90-degree angle. Really similar to the cone one. Okay. So it's not open because, I mean, okay, so proof is very similar to the cone. So P is a point in the hyperplane. Isn't the hyperplane like, wouldn't it be like on the hyperplane? Isn't it kind of, doesn't really have thickness? Well, I guess it has thickness in one direction, but not another. P is a point in the hyperplane, and epsilon greater than 0. P plus epsilon over magnitude of A times A is within epsilon P, but it is not in the hyperplane. What's up, Prime Gamer? I would just show that the complement is open and that literally any ball on the hyperplane doesn't stay on it because you move along A. Just show that the complement is open. And that literally any ball on the hyperplane doesn't stay on it. On the hyperplane doesn't stay on it because you move along A. No, not penetrating deep enough into the brain yet. Okay. Man, I wish I could understand that though. But Big Pepe says, if we've got P in the hyperplane, oh, we get some beef here. Johnny is absolutely roasting Alexander. That method is trash. Yeah, that's what I am doing. I just add small multiple of A to the point on the plane. Okay. All right, so P is a point on the hyperplane, and epsilon greater than 0 and okay, just to zoom out again. So we're showing this is not this isn't open. So the negation of the open definition is that there exists a point, and for all epsilon we choose do we negate the definition of the subset to that it's not a subset? You should probably go for something big. Try to prove P equals NP. In 3D, if I try to draw a ball centered on a point on a plane, some point in the ball is orthogonally displaced from the center. Yeah. Okay, I buy that. All right, so pick a point x1 through n in the hyperplane. Then an epsilon, then adding an epsilon lies in a small ball around the point, but it is not in the plane. Yeah. Oh, never mind. Wait, it could be in the hyperplane. You have to displace in the direction of A to get out of the hyperplane. Because the hyperplane is orthogonal to A. So if A is like that and the hyperplane is like that, if you displace in the direction of A, you're going to go up out of the hyperplane. Whereas if you are in the hyperplane but you go in the wrong direction, you could stay in the hyperplane theoretically. Um, wait, so something about that. So like say that you have your hyperplane and what Johnny is saying with and he is fevered, so we got to be careful accepting what he says. But so if you have a point and then you epsilon you have an epsilon zooming out from one of the coordinates of the point, then you're assuming you went in the right direction, which is the direction of A, then you're good. But why not okay, why not do something like this? Like if you have x1 x dot 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 xn, why not like add epsilon to all of them? Like wouldn't it's just like an impossibility that the hyperplane extends in all directions. It extends in just a subset of the directions. But if you're like radius, if you're epsilon, are you allowed to do that, or do you have to pick one direction to expand from? Yeah, I guess the first coordinate of a vector we're taking the dot product with is 0. But then you just pick a different coordinate. Trying to play around with coordinates is a losing battle. Showing the complement is open. Alright, it looks like Alexander swung Johnny around. Wait, Alexander, are you Greek? Are you the Greek moderator? Or was that some other guy we made moderator? For some reason you're a moderator, which is fine because you're helping out, but showing that the complement is open geometrically is the most natural thing to do. Oh. Huh. The only thing faster is recognizing a hyperplane as the inverse image of a point. Okay, well, so to show this isn't open, xn, x1 to xn, which is in the hyperplane, Can't you just add epsilon to each of the coordinates? Oh, Alexander and I are talking about different exercises. Showing that it's closed while I was arguing for not open. Oh, I see. Wait, why only add epsilon to a single coordinate? Are you not allowed to add epsilon to multiple coordinates? To a coordinate for which that coordinate of the vector A is non-zero. Because they're orthogonal. Thinking in terms of coordinates, v nudges in certain directions is kind of clutter. You can, it will just simply not guarantee that the point lies outside the hyperplane. But I don't understand why that's the case, because if you add it, like if you add an epsilon and the hyperplane is extending, like if you add it to the part of the hyperplane that's extending in the same direction as A, then you've stayed within it. But if you extend it out in all dimensions, it's like impossible, because the hyperplane only extends in, it doesn't extend in all dimensions. There's like a dimension that it doesn't. X was in the hyperplane, lambda times A be a small multiple of A. Okay. Then not that A times X plus lambda A greater than C. Let me write this up real quick. Okay. Wait, I am interested actually in what Big Pepe is saying. X is in the hyperplane. Small multiple of A. A times X plus small multiple of A is in C. Well, a dot product. So X times, so X plus lambda A can't be in the hyperplane algebraically. Epstein is just keeps creeping in somehow. X plus epsilon times a stays inside an R ball centered at x equals 0, or x. X plus epsilon times a. Is that you're judging the point x along A. Assuming A is normalized. Oh, we got a new player, H Ghost. Can you choose x0 and h such that the dot product of your A and the x0 equals c? Then for parallel points, in other words, x0, this is I think what Pepe was saying too, that some multiple of your vector plus x0 can't equal c because the magnitude of A is greater than 0. Oh! We do know the magnitude of A is greater than 0. Oh, I get what Pepe was saying now. Is not in the hyperplane. Oh. Well, it's okay. So, and you say also x plus lambda a is not in the hyperplane because its dot product with a is greater than c. For lambda small enough, we know x and x plus lambda are within epsilon of each other. Oh. Yes. That's why I wrote lambda small enough. Like any sequence xi that converges, the dot product with one parameter fixed is a continuous function. So the limit a dot chi, or x sub I guess, equals a dot yeah, that's the way I did this too. Dot product with one parameter fixed is a continuous function. So a dot xi, and the former is just the constant sequence. Yeah, what's up, H-Ghost? Okay. So I'm still confused by Relma 22's argument, but so basically we say that we've got a bunch of I'm not sure that we're allowed to use. No, actually, no, we haven't reached continuity, so I would assume no. It's not explicitly said, but that would be kind of weird. Oh, sweet. Johnny just dropped. Okay. So let epsilon greater than 0. Let a1, all the way up to an. So, okay, that's our vector, and it's not a 0 vector. Then ak does not equal 0 for some k. Okay. Suppose that's the hyperplane, is in the hyperplane, or suppose our point is in the hyperplane. Define q equals x1, xk minus 1, xk plus epsilon halves k plus 1 to n. Then QA. Oh, then, okay, so that's our point. And then doing the dot product, we're going to have x times a1 plus x sub k minus 1. And then we're going to get this xk plus epsilon halves all the way out. And then we combine it back into a point times an a. Well, epsilon halves times that component of k plus the point a. Okay, and then epsilon halves does not equal c since p in the hyperplane and k not equal to 0. Why specifically is it epsilon halves and not just epsilon? No, don't do component-wise. It's not elegant. I mean, wait, Johnny, are you still there? Why is it epsilon halves and not epsilon? But I guess I get what you're saying. Like, yeah, it's just there's a point in the hyperplane, and then we just yeah, Big Pepe. Just email me with your username. Oh, no, you have to prove it is not open for a not equals 0. But the distance between Q and P equals epsilon halves. So Q is in the epsilon neighborhood of P. So this epsilon ball is not contained in the hyperplane. Why does that have to be epsilon halves? Why not just epsilon? All right, but I guess I'll write. Okay, so a sub k does not equal 0. Yeah. As long as it's strictly smaller than epsilon. Oh, right. Strictly smaller than epsilon. Yeah. 1.001. Wait, Big Pepe, I'm curious like what your solution is. I kind of get this solution now, but you said it's possible without individual. Okay, but this is quite a clever solution. Plus epsilon halves, because that's the equation for the hyperplane, but we've injected an epsilon halves. Isn't in the hyperplane, and then that's my Discord. A dot x equals c, let v has norm epsilon. A dot x plus v v is norm epsilon. Okay. All right, you're fixing a variable. AK times epsilon halves. Oh, times epsilon halves, not plus. Yeah. Equals P dot A plus AK epsilon halves which isn't in the hyperplane. Oh, that plus was fine. What do you mean that plus was fine? We add an epsilon halves. Okay, we add an epsilon halves. But then I see where you meant, I think. Yeah. P times A plus AK. Epsilon halves. which isn't in the hyperplane. Actually, I think I want a new alias. Epsilon neighborhood v sub epsilon. Open parentheses. That's cursed. But I can say P in the epsilon neighborhood Q. Okay. All right. You can't use that if A happens to be the unit vector along an axis other than K. It won't work. Why won't it work? If it happens to be the unit vector Oh, right. Yeah. Yeah. Okay. So we have some vector A. And that C in real numbers is redundant, erroneous. Some unit vector A in there, and then there's some index of that vector that's not 0. We just know because the 0 vector is not in there. And then Q is a point where the kth term, which will nicely line up with the vector and the dot product, is epsilon halves. Well, we add epsilon halves to that. So that's a point outside the plane, because if you dot product, there's going to be an extra AK, well, there's going to be an extra epsilon halves in there, which isn't in the hyperplane. And then since the distance between those 2 points is within the epsilon halves, or well, equals epsilon halves, then that implies that it's less than epsilon. Okay, yeah, that's... For closedness, you should think the same argument as the cone one. And let me think back to the cone. So how did we prove that that was closed? Showing like a sequence. Well, given 2 sequences within the cone, we could construct an inequality that we split. closed, given an arbitrary, we have two component sequences. So, and the reason we do that is because we want to show every limit point is contained. So if you have a sequence in there, you have a sequence within the hyperplane. Its limit is going to be in the hyperplane as well. We just want to show that. Oh, but Alexander has another idea. Well, okay, so it's just really easy to get a distance from a point to a hyperplane. So why wouldn't you use that? F of x, a dot x is continuous using facts about continuous functions. We're not allowed to use facts about continuous yet. Do what Alexander wants. He seems really passionate. All right, reasonable enough. Okay. So using the sequences approach for closedness here. So, because there's a couple different ways that, well, it's easier to give you a list of facts I'm not allowed to use. Okay, so there's like a couple different approaches, I guess, to closedness. Like showing that it contains all its limit points, but limit points have a couple definitions. The definition right below, like the one right here, is different than the convergence sequence. Point X is a limit point of a set. So if we have a limit point that intersects, well, where an epsilon neighborhood intersects the hyperplane at some point other than x, then we want to show that that point is a member of the hyperplane. Hmm. Given some point y on the hyperplane, not on the hyperplane, you can easily show that points inside an r-ball centered at y aren't on the plane. Provided r is the distance from y to the hyperplane. So proving the complement is open. Given some point y not on the hyperplane, points inside an r-ball centered at y aren't on the plane. R is the distance from y to the hyperplane. Y isn't an H, it's in the complement. Typing that every time. Actually, I think I need to make this math. That way I can access fields of it. So an epsilon neighborhood, well, it's not an epsilon neighborhood, it's a ball of radius r. Okay, so because we want to show that the complement is open, which means that an arbitrary point. Yeah, so if our arbitrary point y has an epsilon neighborhood, which it does, which is just going to be the distance to the hyperplane. And the distance to the hyperplane right, plus something orthogonal to it. And what's the distance away? Is it just a? Distance can be computed by projecting y onto a and then thinking a little. Projecting y onto a. Okay. All right, if y basically you shift y by a multiple of a till the point is in the hyperplane. I mean, don't we need to know the distance though to provide an epsilon? So I guess I'll write this out unrigorously, but so we're showing that the complement is open. So y is in the complement of h. You could just take like using a ball, using a neighborhood with the with epsilon like equals half the distance, to the hyperplane. That's the short way. The idea is that you're nudging y in the direction of a by some distance lambda will put you onto the hyperplane. Okay, this for any point not on H, the orthogonal projection is unique. The actual distance isn't important. Yeah, I guess I'm having a hard time visualizing this, but in essence, isn't that what you're doing, is just claiming we have distance to the hyperplane if a point's not on the hyperplane. And if you just take your epsilon to be half that distance, you're okay. Distance can be calculated. It's not that important though. For any point on not on H, the orthogonal projection is unique. The orthogonal projection on H. Yeah. Or in 2D, a hyperplane is just a line. It's easier to take epsilon to be the whole distance. Yeah. Yeah, I am thinking the hyperplane is that it's just like the vector A that's defining it is like orthogonal. It's coming up from. It's easier to take epsilon to be the whole distance. because it'll be algebraically more elegant. Why should it be less? We have strict inequalities everywhere. Yeah. Okay, and if you were going to do the algebra out, that's the essence of the solution. You would do the algebra out with the distance function, and then you'd have a more specific epsilon. Because if epsilon equal to the distance, the projection is within epsilon. Because if epsilon is equal to the distance, yeah. Zeus interlude. You have to study 17 hours a day or else you'll never get a job the way things are going. Remember A is a free vector, so given some point y not on H, there is some real lambda such that y minus lambda A is in H. Alright, thanks for the help, Big Pepe. Thanks. Okay, remember A is a free vector, so given some point y not on H, there is some real lambda. Y minus lambda A is in H. Kissing, not kidding. Open ball radius 1 around 1, 0, 0 is kissing the plane at x equals 0. But we're trying to prove that this is open. So which means that every point has an epsilon neighborhood. So even points that are right up against it, that are like right on the edge of the hyperplane, well, arbitrarily close, half the distance. I think my like linear algebra picturing abilities are, and my intuition about vectors isn't as good as it should be. It's been a while since I've taken linear algebra. But I don't know. I think I have. I suspect this answer will get me full credit knowing my professor. But yeah, knowing that the algebra more rigorously would be nice. X equals D times the normalization of a squared plus q, where dot q a dot q equals 0, d not equals c, vote Cauchy-Schwarz. All right, I mean, I'm just going to come back to this in more detail later, I think. We know that this is closed, and is it bounded? Could all be done with a teeny bit of algebra. Okay. All right, the algebra yearns to be done. All right. Yeah, I guess I'm just not sure of the algebra approach is only a teeny bit. What's the distance to the plane though? Where is my OBS? It's norm q, where q is the component of x in the orthogonal complement. Solve the equation I gave for lambda. It's norm Q. In the orthogonal complement. Yeah, I mean, I don't know. My linear algebra is quite rusty. Which luckily I don't like. This problem isn't okay, so the distance c minus y over c minus y dot a over magnitude of a. It's a good exercise in visualization. Yeah. All right. And that distance, oh, I need parentheses. So if this is our epsilon neighborhood, then we want to show that an element of it, or an arbitrary element of it, is in the complement. Man, this intuition is slow to build. All right. Epsilon is less than that distance. What's left in the algebra? Oh my brain is so melted at this point. All right, yeah. Honestly, like, I can't think much more. I'm gonna call it a day here. At least